Okay, here's a more difficult projectile motion question. This is choosing a vector to hit a target. You hold a ball at a height of 2 meters. You're 5 meters from a basketball hoop, that's horizontally, which is 3 meters high. Find the velocity for the ball to go into the net. So drawing a quick picture here, you're holding the ball, so I guess that's you're holding the ball, and you must be pretty tall here. It's at a height of 2 meters, that's 6'6". So the ball's here, it's at 2 meters high. It is 5 meters from a basketball net, and the basketball net must be just under regulation because it's 3 meters high. So there's the basketball net, there's the ball, it's at a height of 2 meters. And what we want to know is an initial velocity that will cause the ball to follow a trajectory where it lands in the hoop. So I'm going to break this problem into vertical and horizontal component. So I'm going to start out vertically. So vertically, the displacement of the ball in the y direction is 1 meter. We're starting at a height of 2 meters. We have to finish at a height of 3 meters, so we've got to go 1 meter up. I've not given the velocity vector, so we don't know, but we know we're going to need an initial velocity in the y direction. Acceleration due to gravity is 9.8 meters per second squared. So I really don't know initially what my velocity is going to be, and the truth is there are many velocities. You could throw the ball really fast, really high, and it could come down. Or you could throw it a bit slower but at a lesser angle. Or you could throw it really fast at a much lower angle. It'd be hard to get it to go in, it would probably bounce out, but in theory there's an infinite number of velocities that will get you there. We just have to find one. So I'm going to choose a velocity, an upward velocity, so only the vertical component of my velocity, and I'm going to choose it to be 5 meters per second. Now this may or may not work. 5 meters per second might be sufficiently fast to get the ball to this height, and it may not be, but we'll quickly find out. So given that we're throwing the ball 5 meters per second upward, up a height of 1 meter, while it accelerates downward at 9.8 meters per second squared, displacement is initial velocity times time plus half acceleration times squared. So 1 is equal to 5 delta t minus 4.9 delta t squared. Okay, so we're going to put this into the quadratic formula and determine at what time the ball is at our required height. If there's a solution to this, it's probably going to give us 2 answers, and those 2 answers would correspond to the ball being at the same height as the hoop on the way up and on the way down. We're going to take the second one, that's when it's on the way down. So delta t is negative 5 plus or minus the square root of 5 squared minus 4 times negative 4.9 times negative 1. This is going to work. All over 2a, so that's negative 9.8. Here's how I know it's going to work. 4 times 5 is less than 5 times 5. If the velocity I chose, the initial upward velocity, was too slow for the ball to get at the hoop, I would know because when I tried to solve this quadratic, I'd be taking the square root of a negative number, meaning that there's no real answer. But in this case, 5 squared is 25, 4 times 5 is 20. I'm going to have about the square root of 5 in here, so this is going to work. So delta t is negative 5 plus or minus 5 squared is 25 minus 4 times 4.9. I just turned it to a positive because I got a negative times a negative. That gives me 5.4, and its square root is 2.32. So my two answers are going to be 0.27 seconds or 0.747 seconds. So the way I'll interpret this is after 0.27 seconds, the ball is at the height of the net on the way up. And after 0.747 seconds, the ball is at the height of the net on the way down. That's the one I'm choosing. So what this means is with an initial y component of my velocity at 5 meters per second, I'll be at the right height after exactly 0.747 seconds. So I'm now going to take that and do horizontal analysis. Remember, horizontally, our displacement is 5 meters. Our horizontal component of our velocity, we don't know. And the amount of time that this takes, we've just determined, will be 0.747 seconds. Now, there's no acceleration horizontally. Strictly speaking, there'd be a bit of air resistance slowing the ball down, but we're going to ignore that because our speeds are relatively low. So the velocity in the x direction is going to be 5 meters forward divided by 0.747 seconds. And that's 6.69 meters per second forward. Now remember, we chose vertically, and this was the only guess here, the only choice. We chose vertically to throw this at 5 meters per second upward. We determined if we do, it's going to take 0.74 seconds to get to the height of the hoop a second time, and for it to go the horizontal distance required in that amount of time, we need the horizontal component of our velocity to be 6.69 meters per second forward. So the velocity of the ball has got to be the result of throwing it forward with 6.69 meters per second, while at the same time throwing it upward at 5 meters per second. Forward and upward are 90 degrees from each other, so we can just use the Pythagorean Theorem. And I'll put a 1 there. This is the initial velocity. So it's going to be the square root of the sum of the squares. And then the angle is going to be inverse tan of 5 over 6.69. Okay, so our final velocity is 8.35 meters per second at an angle of 36.77 degrees, and that would be upward from forward. Now, given the initial question, this is not the only right answer. This is just a possible correct answer. Because remember, there are many velocities that would get this ball into that hoop. But for each velocity, there's only one angle that would correspond correctly with it. So once you choose your velocity, you have to calculate your angle. And the way I did this, I chose the vertical velocity. I found the amount of time it would take for the ball to rise and then fall and end up at exactly that height. And then I used that time to determine how far forward how fast the ball must travel forward to also arrive at that point in that same amount of time.